Okay, today we're going to look specifically at the work done by the gravitational force. Let's start with the tomato that is thrown upwards in the air. So it's moving up. As it moves some distance d in the air, let's look at the work done by the gravitational force. So the only force acting on the object right now is the force due to gravity. So if we look at work, work is by definition the force dotted with the distance. So that is going to be Fg, force due to gravity, times distance, times cosine of the angle between the force and the distance direction. So this is going to be mg times d, cosine of that angle. Well, that angle is 180 degrees because the distance is up, the force is down. So this is going to be negative mgd. So that is the amount of energy that is transferred from the kinetic energy of this tomato out of the system. So we would have a final kinetic energy that is much lower than what our initial kinetic energy was. Now what if we had a particle-like object and we applied a force to it in order to raise it some distance? So there would be at that point two forces acting on the object. We would have a force due to gravity down, and we would have an applied force in the upward direction because we're moving it upwards. At that case, if we move it some distance d, so now it's way up here, some distance d away, then we have a couple of different works happening. We have the work due to gravity, which is going to be mgd, and that's going to be negative because the force due to gravity opposes that direction of motion. We're going to have a work from the force that we have pulling on it, and that's going to be the magnitude of the force that was applied times the distance. The angle, they're in the same direction, so it's going to be 0, and cosine of 0 is 1. Now, if we know that we are moving with a constant velocity, then we know that the force that we apply is equal to the force due to gravity, in which case that would be mgd. So that's if the velocity is constant. So in that case, the net work that's applied, the network acting, the total sum of all of the work is going to be 0. So that tells us that the change in kinetic energy for the system is going to be the sum of all the work. So it's the work from the applied force and the work from the force due to gravity. And if we have any other forces acting on it, we're going to add the work done by those forces as well. So let's look at an example. Okay, so here we have an inclined plane, and we have an initially stationary piece of cheese. And that crate of cheese is going to be 15 kilograms. It's going to be pulled via a cable a distance along the incline. So we've got a cable pulling it up the incline, and it's going to come up some distance d, where d is going to be 5.70 meters. Now this is going to be a frictionless incline, so that means that there is no friction, nothing. So we want to know how much work is being done. Well, we do know, we are given that the vertical height here, the vertical height that's we're traveling here, is 2.5 meters, and it's going to stop there, so the velocity is going to be 0. Now we need to know first how much work is done on the crate by the gravitational force during the lift. So let's calculate that. So the work done by the force due to gravity, well, that's going to equal the force due to gravity times or dotted with the distance. Now the distance that's in the direction of travel is going to be 2.5 meters. That was broken out for us. So we know that this is going to be negative a mass of the wheel of crate, the cheese wheels in the crate, times gravity, times that 2.5 meters that we were given. So we're going to have negative 15 times 9.8 times 2.5, and that's going to be negative 367.5 joules. Now, another thing that we could find is how much work is done on the crate by that force, the tension in that cable that's pulling this up the incline. So what we know, the work done by the tension force, that's going to equal the force tension dotted with the distance moved. So the force tension, we need to find that. Or do we? Now, one thing we do know, we know that the crate is initially at rest, and we know that when it stops, it's at rest. So what we do know is that the energy that it's put into the system by the tension force, well, that's going to be interesting. So we've got the change in kinetic energy is equal to work. That's the work kinetic energy theorem. The change in kinetic energy, kinetic final is 0, kinetic initial is 0. So there's no change here. So this is going to equal the work by the tension force plus the work by the gravitational force. So that tells me the work by the tension force is going to equal 367.5 joules. Now from that, if I needed to, I could actually come back and find what that tension force was. I could come back here and I could substitute the 367.5 times the force tension. We know the tension force is up the incline. The distance we moved here is up the incline. So we'd have force tension times 5.7. Cosine of 0 is 0. So we could actually calculate what the force tension force would be. So if we divide the 367.5 by 5.7, what we're going to get is approximately 64.47 newtons. So that gives us another way, if we need to, that we could come back and calculate what those forces are. So next time we're going to start looking at non-constant forces. We're going to start looking at springs.